So this is another video about vector spaces, which I know everyone loves, vector spaces. Okay, so what did we say last time about vector spaces? Well, we said the vector space is really just a set. It's a set, which is a collection of elements. It says, whoa, that does not look. Let me just rewrite set. So it's a set, which is just a collection of distinct elements that we call vectors. And a vector space also contains a field, or we also like to call them scalars. Okay. And for any vector space, there are two basic operations that are defined. So we always define two basic operations. Operations, which are, as you probably recall, vector addition, and scalar multiplication. Okay, so those are the two main operations that are defined, and then we have 8 axioms to check. 8 axioms to verify. Okay. Okay, so that's basically an overview of what we did. Okay, so what I'm going to give you in this video is an example of a very commonly seen vector space. So, example of a vector space, we usually call it Rn. Okay, and Rn is basically the set of all n by 1 excuse me, n by 1 vectors with field R. Okay, so what that means is that my Rn, my vector space Rn, is a set that looks like a vector with n number of rows. So I have, these are my rows here, so n number of rows and one column. Okay, so I have one column, so I can write them as A1, A2, A3, and so on until AN. So n denotes the last entry. That's AN because we're at the nth row. So it's any general type of vector that looks like this guy, such that A1 through AN belong to the real numbers. So that's what we mean when we say that the field is R. Okay, and how are the two basic operations defined? Well, so for vector addition, vector addition is defined as follows. If we have x, which I'll represent as x1, x2, xn. So notice I have n number of rows here, as I go until xn, plus y, so I'm adding y, oh, that's so weird looking, plus y, I'll get, so y I'll define as such, and this is my plus operator. So when I add these two vectors together, how we define it in Rn is we say that we take the first component of x and add it to the first component of y. In other words, we get x1 plus y1, which is just an addition over R, over the real numbers. And then for the second row, we get x2 plus y2. And then that continues until xn plus yn. And that's how we define vector addition in Rn. What about scalar multiplication? Well, scalar multiplication is just as simple. So if I take a scalar c, right, a scalar c that belongs to R. So I probably should have said, so here I'm saying x and y belongs to v. So here I'm saying c belongs to R, and again, x belongs to v. So c scalar multiplied x is going to be c scalar multiply x1 through xn. And what that really is, it's just c times x1, c times x2, and so on until c times xn. And here, these multiplications are actually just multiplications over r, over the real numbers. So these are just multiplications over r. Now, if I didn't tell you that this was actually a vector space, after doing this, so this would basically be what would be given in the question. Okay, so this is sort of like this, all of this is given. Okay, all of this is given. What you would need to do is you would need to verify all 8 axioms. So to show that it's a vector space, so to show that this was a vector space, to show vector space, I'll just write to show a vector space, we would have had to prove all 8 axioms. Okay, and I'm not going to prove all 8 axioms because that would be a much too long, much of a very long video. But what I will do is I will prove some of them, not all of them, but I'll prove some of them. So the first one I'll do will be, I'll do the first one. So what does axiom 1 say? Well, axiom 1 says that you want to show that for all u and v belonging to my vector space V, u plus v is equal to v plus u. Okay, let's see how we can apply this to Rn. So now, how you start the proof, you would say something like, suppose x and y belong to Rn, right? As soon as you write that x and y belong to Rn, then you can say that by definition, x is equal to x1 dot 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 xn. In other words, it has n rows and 1 column, and y is equal to y1 through yn. So again, n rows and 1 column. So n components. And so both of these are n by 1 vectors. Okay, so now let's try to see if this property holds. Okay, so what is x plus y? Well, x plus y, we just defined it over here, right? We just defined it over here. It's just equal to x1 plus y1, x2 plus y2, until xn plus yn. Okay? But what we know about the real numbers, so in R, we know that a plus b is equal to b plus a. We know this as a rule. We know that commutativity is always true in R. So for instance, if I do 1 plus root 2 in R, well, that's the same as doing root 2 plus 1. We know that's true. We could check it numerically, but we just know that this is true. To prove it is another story. So what we can do, because this sum is actually over R, what we can do is we can just apply that rule, and we can say that it's equal to y1 plus x1, y2 plus x2, and so on until yn plus xn. And when I get to that step, what I can do is I can now separate my vector as y1 through yn plus x1 through xn. And this is in fact what I wanted it to be, which is x, y plus x. So what we have really is we end up with x plus y equals y plus x, right? And this proves axiom 1. So axiom 1 is proved. Okay, so that's how we would prove axiom 1. Okay, let's do another one. So let's do the, well, let's say axiom 3, which is the existence of a zero vector. So this says that there exists a zero vector such that for all u belonging to V, right, u plus the zero vector equals u. Okay. Well, let's see if this is true for Rn, right? So if we say, let, if we say, you choose different color, let x belong to Rn, then we know by definition that that means that x is equal to x1 through xn, right? Now, on existence proof, what you typically tend to do in these cases is you say, okay, well, suppose the zero vector is what you think it should be, which is 0, dot 0. So you have n zeros, right? Remember, this is an n by 1 vector. This is an n by 1 vector. So you'll have n zeros, n rows of zeros. Okay. So if we actually do x plus the zero vector, then we write this out. So always write this out, do it step by step. So that's equal to x1 through xn plus the zero vector, which is just a bunch of zeros, so 0. And if we add this, we said that we defined the addition operator, right? So we defined this operator in Rn as you add this component to that component, this component to that component, and so on until this component plus that component. Okay, so what you have to do essentially is you add x1 plus 0, and you add x2 plus 0, and so on until xn plus 0. But we know that over R, so over R, if you add a plus 0, so this is the 0 in R, then that's equal to a. So for instance, if you do 2 plus 0, well, that's still 2, right? We know that. So that means that in this scenario here, this actually simplifies to just x1, and this just simplifies to x2, and so on until xn. So what we really just get is x1, x2 through xn. So what do we actually have at the end? We just finish with x. Okay, so we've proved that x plus the zero vector is actually just equal to x. So that's proved. So that proves axiom 3. Now let's do maybe one last one. Let's do axiom 7, let's say. Okay, so what does axiom 7 say? So axiom 7 says that for all u and v belonging to v, and for any scalar c that belongs to the real numbers, if I do c times, or scalar multiplied, u plus v, then this is equal to c scalar multiple u plus c scalar multiple v. Okay, well, it looks like what we need in this proof is 2 vectors and 1 scalar. Okay, so let's say suppose c belongs to R. Okay, so like in the actual axiom, and I'll use x and y as before, and x and y belong to Rn. Okay, so again, what does it mean if I say x and y belong to Rn? Well, that means that I can automatically write that x is equal to x1 through xn. This is just by definition. And y is equal to y1 through yn. So this is the vector. So this you could write, this is by definition. Okay? So then I'm going to write, I guess I'll start with the left-hand side, right? So the left-hand side of my proof is I have c, which is an arbitrary scalar, times, and then I have So I'll do two brackets. So I'll do a big bracket and then a small. So I have x, so this is my x, so it's x1 through xn plus y1 through y. Okay? So then what do? Well, I know that this is just an addition over Rn, and I know what the addition over Rn is. It's just you add each component to itself. So it's just equal to c times x1 plus y1, y2 plus y2, and so on until xn. Well, I was saying y1 plus y, sorry about that, x1 plus y1, so x1 plus y1, x2 plus y2, and so on until xn plus yn. Okay? And now I have a scalar multiplication, right? So this over here, this is a scalar multiplication. And scalar multiplication is also defined over R. So the definition, I won't go back to it, I'll just remind you, it's if I have something like this, then I can actually just multiply each component by C. And that's what I'm going to do in the next step of my proof. So I'll write that this is equal to C times x1 plus y1, and then the second row is C times x2 plus y2, and so on, and then the nth row is C times xn plus yn. But now what you have to remember, and sort of the basic idea of all these proofs, is that once you get here, well, this is actually over R. And we know that over R, C times A plus B is equal to CA plus CB. For example, if I have 2 times 3 plus 5, well, I know that that's equal to 2 times 3 plus 2 times 5. I know that's true. Okay, well, that's what I'm going to use. I'm going to use that fact to rewrite it as CX1 plus CY1, and then CX2 plus CY2, and so on until CXN plus CYN. Okay? And then, okay, so that's it. Now what I'm going to do is, because what I'm trying to get at, remember, trying to get at something that looks like this, right? Something that looks like C times U plus C times V, or C times X plus C times V, or C times Y. So the next thing I'm going to do is I'm going to separate these, because if I know that addition goes both ways. So what I mean by that is, if, say, in this case, if I can go this way in my definition, if I can say that if I add x plus y, then this is x plus y, well, I can go the other way. I can say that if I have x plus y, then I can decompose it into x plus y. I know I'm just saying the same thing over again, but it makes sense in terms of the definition. Okay, so let's go back to where I was here. Okay, so that's what I'm going to do. I'm going to decompose this into two vectors. So I'm going to have cx1 through cxn plus, then I'll have cy1, y1 through cyn. Okay, and then my before last step is going to be working backwards with the scalar multiplication definition, because if I can multiply each one, then what I can also do is I can factor. So I can factor C. So what I'm going to do here is I'm going to factor C. Okay, I apologize for my handwriting. So I'm going to factor C in my next step. So it's going to look like C times x1 through xn plus C times y1. Okay, my y won't write, through, oh, come on. Okay, so let me write it a bit more to the left. So it's equal to C times x1 through xn plus c times y1 through yn. And I know by definition that this is cx plus cy. So even though this proof seems trivial, well, I mean, it seems long, but it actually is quite easy and quite trivial. You just have to get the steps right. So you have to realize that when I get to my left-hand side, I just use the definition here. I know that x and y is x1 through xn, and that y is y1 through yn. And then here I use my definition of vector addition. So this is the vector addition definition, And then here I use my definition. So here I use my definition of scalar multiplication. And so I distribute my c to each component. Then here, this is the key part. The key part is realizing that now it's over R. So I can use the distributivity law in the real numbers that says that c times a plus b is equal to ca plus cb. So that's what I do in this step, okay? And then I separate my two vectors because really I have two vectors here. I have one vector and then another vector. So I separate them, I factor the c. So this is factoring c. And I end up with cx plus cy. So what I've done now, I've shown that cx plus y is equal to cx plus cy, proving axiom 7. And the other proofs are really similar. I just wanted to show you how you would sort of go about proving these. So I hope that helps.